Hello everybody, thanks for joining us today. In this session we want to solve another problem from chapter 3 of the book Heat Transfer, 10th edition of Heat Transfer from Mr. J.P. Holman. Okay, let's go to the problem and solve problem number 39 from chapter 3. Okay, considering the one-dimensional field problems of chapter 2, show that a nodal equation for nodes along the field in the figure 39, in this figure, may be expressed as this relationship. Okay, this is Tm multiplied by H as a thermal coefficient, heat transfer coefficient, P as perimeter, delta X. You can see delta X here, squared, and K as thermal conductivity, and A as actually area of this cylinder or any other shape, but area is A, capital A, plus 2 minus HP delta X squared divided by Ka multiplied by T infinity. T infinity is temperature of this fluid, and minus T in point M minus 1, this point, plus T temperature at point M plus 1, this point. Okay, temperature of this point and this point is equals 0. Then we should actually show the nodal equation for nodes. We can earn this equation. Okay, let's go to the whiteboard and get started and find the relationship. Okay, first I want to again, like always, let me draw the picture, okay, which is something like that. A point here, a point here, point M is here, and M plus 1 is here. Okay, and this is M minus 1, and the actually distance between these 2 points are delta X as this distance. All are equal and delta X. So a fluid is around the fin. Okay, and this is continuous, not important what is the distance and length of the fin. Then T infinity is temperature of here, and P is perimeter of this one. For example, if a cross section would be circle, the perimeter is PD. Okay, for circle cross section. Okay, this is P as perimeter. Okay, and this is base of fin, of our fin. Okay, then I will write the equation again. Tm multiplied by HP delta X squared Ka plus 2. It's better to write it again carefully, minus HP divided by Ka delta X squared multiplied T infinity minus Tm minus 1 plus Tn plus 1 equals 0. Okay, this is our relationship. We should drive this equation. Then let's go and do it. Okay, I can write for an element, I can write energy in left phase, for each element. Okay, for example, here and here, or for one of the elements. Okay, because we have Q here and Q go into the element and go out from that element too. Okay, then I can write energy in left phase equals energy in right phase, but some of energy will transfer to the fluid. Okay, then plus lost energy by convection, lost energy by convection. Okay, then I will write the equation for this one as we had it in chapter 2. You can refer to the chapter 2 and see it. Okay, then if I want to change the color of my marker and write this equation, minus Ka dt over dx, which is heat transfer from thermal conductivity, equals minus Ka dt over dx, and plus, for here I want to explain something. Okay, so for example, we have an element, we have Q here, which is Ka delta T dt over dx. Okay, but this Q is Q plus dq. Okay, then we should write this dq. If imagine a diagram, and this is temperature profile of that. Okay, we assume here this is alpha equals tangent. Okay, tangent, this is alpha. Okay, then tangent of alpha equals, for example, this is dq. Okay, or it is better say if it is t and this axis is x. Okay, here is dt over dx. Okay, this distance, let me just write it bigger than this. Okay, this is t, this is x, this is alpha, here is dt over dx, this is the dt. Okay, and this is x dx, and this is dt over dx. Yeah, then tangent of alpha will be dt. Okay, just let me name this distance a. Okay, a divided by dx. A equals tangent of alpha, which tangent will be dt over dx. Okay, tangent of alpha is dt over dx. The slope of this diagram will be tangent of alpha, then multiply by dx. Okay, dx. Okay, but if this axis would be dt over dx, it would be, here would be the 2x of the 2x of the x2. Okay, yeah, then I should write this. This one, this is a, and from here to here is dt over dx. Then I would write dt over dx plus d2t over dx2 multiplied by dx. Okay, this was affirmative of d2t over dx2 dx multiplied by dx. Okay, then plus energy, lost energy by convection, HA delta T, which delta T is T. This T is T of wall, okay? T of this wall. Minus T infinity, okay? T infinity is temperature of infinity. And in place of A, we can write P dx, okay? Well, this is perimeter, and if this cross section would be circle, it would be, this P would be PD, PD as diameter, PD multiplied by delta x. Okay, it's better to write delta x. Okay, then let me erase this one because we don't need that anymore. Okay, and I will erase this and write P delta x. Okay, then this will eliminate these terms, then minus Ka d2t over dx2 dx, this is this one multiplied by minus K thermal conductivity area, plus HP dx T minus T infinity equals 0. Okay, then I can write, okay, d to t over dx2 minus HP Ka T minus T infinity equals 0. Okay, then I can write T equals T to T, D to T, dx square Ka HP plus T infinity, which this is finite the difference method. This finite difference equation of this problem, we should write this formula like that one. Okay, so first let me just I should derive a form for finite difference equation. Then dt over dx in point of m plus 1 over 2, okay, which is here, this point. Okay, m plus 1 over 2 is here, m plus 1 over 2. I wanna find slope of T, temperature in this point. I would write it in this way, T of m plus 1 minus T of m. This is T of m and this is T of this. Temperature of this point will subtract temperature of this point from temperature of this point, and divided by the distance, which is delta x. Okay, I can write it for actually another point, which is m minus 1, 2 here. Okay, middle of these two point. This is element, our element. Okay, m element. It is equals actually Tm minus Tm minus 1, temperature of this point minus temperature of this point, divided by delta x. Okay, and for second order of derivative of x, I can write actually in point m equals this one minus this one, dt over dx, okay, from n plus 1 over 2 minus dt over dx, the endpoint of m minus 1 over 2, okay. It is equal, it will be equal if because those denominator are the same, I can subtract these two from each other. It could be tm plus 1 plus tm minus 1 minus 2 of tm, okay, divided by what? Delta x square, okay, and it has a delta x here. It should be derived by delta x because this distance from this point to this point is delta x. Then it would be delta x square. This is actually the 2t over the x. Finite difference. This is finite difference formula. I should use it to solve this problem. Okay. Then oh, I made a mistake. I shouldn't raise that. Okay, no problem. I'll write it again. Okay, it was t infinity oh yeah, equals, yeah, okay, oh no, I don't need it, actually, I don't need it. I just needed a formula that I derived for you. This t equals the dot t dx square k a dx2, okay, sorry, k a hp plus t infinity, okay. This is a finite element form. I should substitute this one from this one, okay, to earn that, okay. Then Tm, which is temperature of the point M, equals this one. I should put this one, substitute this equation in place of this one, okay. Then let me write it. Tm plus 1 plus Tn minus 1 minus 2Tm divided by delta x square, okay, Ka Hp plus T infinity, okay. Then I would change this form to this one, Tm delta x square plus 2Ka Hp equals Tm plus 1 plus Tm minus 1 Ka Hp plus T infinity delta x square, and then it would be the hour form in the problem. You can see it here, okay. This is exactly thing I want. Tm Hp over Ka delta x square plus second plus 2 minus Hp Ki multiplied by x delta x square T infinity minus Tm plus sorry, this is minus 1 plus Tm plus 1, okay, and this is equal 0. Okay, this is our relationship as you can see it at the book, at the problem. This is exactly this one. Okay, it was this temperature of actually we can use this relationship to find temperature of M, point M. Okay, and this is relationship that we have it here. It was solution of problem number 39. Thanks for watching this problem. I hope you enjoy and take care. Have a good time. Bye bye.